In this video, we're going to look at our second day of capacitors, and actually our second to last day for the extra topics unit for AP Physics. Last day, we were finishing up looking at what happens when you discharge a capacitor and how the charge leaves at first at full voltage, and then as the charge continues to leave, the voltage of the capacitor starts to drop off, and that affects the rate at which the current's going to flow, so it actually slows down its discharge rate as time goes by. What we're going to look at now is how much energy is actually in the capacitor when it's charged. So let's say I've taken a battery and I've charged up a capacitor, so I've got lots of Q stored up on this parking lot, right? These double sheets here of tinfoil. So it's all charged, ready to go, and I'm going to go and connect it up to this light bulb, and I'm kind of wondering overall at the end of the day, and it really will be the end of the day, you'll have to wait forever, but if you discharge this capacitor, which does technically take forever, and the current flows very fast at the beginning and then slower later on, how much energy is there actually in this device, in this capacitor? And what we know is that there's this relationship for how much charge you can get on. Q is equal to CV. It's really also a relationship that tells you how much voltage there would be at any charge level. And so if you look at how much Q is remaining on the capacitor and then that voltage, right, what you're going to find is it's this nice linear relationship, and it's going to actually go and descend downwards. So you start off with this maximum voltage out here, maybe we'll call that like Vmax, with all of that Q that you ever get. And then as you run that light bulb, that set of values for Q and V starts dropping along that line, fast at first and then slow later on. And what we're going to try to do is figure out overall how many joules of energy can we get out of this device. So just kind of highlighting here again, the first charge, the first little bit of Q that leaves, it leaves at full voltage. So the first charges leave at full voltage. But not all of the charge leaves at full voltage. It does start to drop off, and it becomes less and less and less and less. So let's think about what this is going to look like as we work our way down that graph. At some point later on, there just won't be as much charge left on this capacitor, maybe only that much, with the corresponding negative charge down here. We're still connected, we're still going to get some current flowing, but now this current is going to flow slower, and it doesn't have the same voltage that it had before. If you think about that graph where you've got, hey, here's how much charge there was based on the voltage we used to push it on, then we're still on this line, but now we're down here. And so these Qs, as they leave, they're at a much, much lower voltage. Okay, so just some points here that we can add. Just trying to get the math story right. First little issue, as the Qs leave, as the charges leave, the voltage drops. And so later Qs have lower voltage. They're not going to light up the light bulb as bright. The last Q to leave, which is quite a while down the road, but the last Q that leaves has 0 volts. On average, as you watch those Qs leave with their voltage, the average voltage that they have is equal to 1/2 the maximum voltage that we ever saw from when that capacitor was fully charged. Well, this whole page was supposed to be figuring out how much energy is there actually stored up in that capacitor. Well, I'm looking for joules, right? That's how energy works. And I know that I can get there by taking charge, which is measured in coulombs, and multiplying by voltage, which is joules per coulomb. So I'm going to go with my charge that was on that capacitor multiplied by my average voltage as they leave, which is half as much as the maximum voltage. So you could say, okay, well that's going to be 1/2 times the Q that was on that capacitor multiplied by V. And when I just write in V here, I mean V max, because we're going to say, yeah, hey, look, here's a capacitor. It's fully charged with a voltage. Great, how much energy is there for that maximum voltage? Well, I also know that Q is equal to CV. So I'm just going to go and make a little substitution here for that Q. And there are a few other ways now that I can rewrite this. I can say that that's equal to 1/2, and then I could write that as capacitance times the voltage multiplied by the voltage, right? So just putting in CV for the Q, or maybe the most common form you'll see, 1/2 the capacitance times the voltage that you're at squared. And so that idea right there, that's how we can go and find out how much energy there is in this capacitor. We can go with 1/2 the capacitance times the voltage that you're charged at squared. Okay, the next couple of pages, let's look at what happens when you wire up capacitors in parallel or in series. So remember, these are like parking lots for charge. So if I wanted to connect them up in parallel, that's an option. I can do that. Attach a little wire here and over to there, and then maybe we'll go over to our battery. Same thing on the bottom. We'll link those together, and then we'll go back to our battery. So that battery is going to act like a pump, and it's going to create some positive charge here and some positive charge there. Not as big of a parking lot. And then we've got our negative charges as well. All right, so essentially what's happening here, by putting these capacitors in parallel, it's like you've made a bigger sheet. It's like you've made a bigger parking lot. And that's what's going to affect the value for the overall capacitance that we've got. So this combination, this parallel combination, essentially increases the area. There was definitely a calculation of capacitance that involved the area of those sheets, and if you have a bigger area, you're going to have a better value for C. Remember, the equation did look like this. If you were just a person making capacitors, the capacitance was equal to this thing called the dielectric constant, which just depends on the material that's in between the sheets. Let's say it's just air, so it's 1. There's this constant of nature, permittivity of free space, and then there's the area of the sheets. There it is, and then the gap. So I'm assuming that the gaps are the same size. Turns out this issue is true in general, but if we can increase the area of this device by having multiple sheets side by side, then we're definitely going to see the capacitance actually go up. So something I can tell you is always true. Two capacitors in parallel always have more C, more capacitance than either one. You always gain capacitance when you put another one on in parallel. You're just simply increasing the parking lot size. And so the equation that you can use to calculate capacitance that's in parallel, it's actually just capacitance 1 plus capacitance 2, literally increasing the parking lot size. Now, this is not like resistors that were in parallel. Okay, so just be careful with this. Worth a note here. Not like resistors in parallel. But I've heard this story before about, oh yeah, yet another one, it's always more, and you simply go, R1 plus R2, but that was when resistors were in series. So this is, air quotes here, this is like, it is similar to resistors in series. Okay, well that's interesting. Capacitors in parallel behave like resistors in series. I think I know what's coming next. All right, and let's go and take a look at what happens if you choose to put your capacitors in series, one after another. Okay, this is where the geometry gets a little bit interesting, and there's some cool physics that's going to happen in this story here. But the result is probably what you're already expecting. Oh, sorry about that. Got this right here. Okay, so I'm just going to go and wire these capacitors up so that we can actually connect them in series. Going to take a wire and attach it here. And then after that capacitor, I'll take a little wire to link those two plates. And then we'll go and make our way back to the battery. All right, so that battery, it's going to behave like a pump, and it's going to create positive charge here, and it's going to create some negative charge here. And you're like, whoa, wait a minute. Aren't you supposed to put that on that other bigger plate? Well, yeah, it turns out when you make that left big plate positive, you will actually get some negative charge here, but you have to think about where it comes from. It actually comes from stealing some electrons from this plate. There's nowhere else it could actually be. These two plates right here that are linked with this wire, they're sort of on a little electrical island, right? They're not actually electrically attached to the rest of the circuit. You've got a big sheet, a small sheet, and a little wire connecting them. And so they are literally on a little insulated electrical island, and they will always have the same amount of charge. So whatever Q you see here, whatever negative Q you see there, you'll see the exact same Q here. Worth a note for sure. So these two caps, in general, those two capacitors, they will, if they're connected like this, they will have the same charge. So whenever we talk about the charge of a capacitor, we're talking about how big is the positive charge on one plate or how big is the negative charge on another. We don't add those two numbers together. We just say, oh, you've got, negative 4 coulombs on one plate, you've got positive 4 coulombs on the other. Yeah, you've got 4 coulombs on that capacitor. Okay, so what's happened here when we do this? It turns out that you've actually kind of made this story worse in terms of capacitance because there's a gap here and then there's another gap here. And you've basically made the gap bigger on this overall combined series capacitance, worthy of a note. Okay, so this combination, this series combination, increases the gap. And that means there's going to be less capacitance in this story. Because the equation for capacitance, just speaking in generalities, is this dielectric constant, that's a 1 if we're using air, permittivity of free space, and then there's the area of the plates, and then there's the gap size. And if you go and increase the gap size, then you're going to be lowering the overall capacitance in this story. So here's something that's a truth that is always going to be correct. Two caps, two capacitors in parallel always have less C than either one. The equation for calculating overall capacitance when things are in series, you can probably guess it because this is, after all, just like resistors but backwards. So 1 over the total capacitance in series is equal to 1 over capacitance number 1 plus 1 over capacitance number 2. So again, not like resistors in series. But it is all backwards. It's consistently backwards. It's like, again, I'm going to use air quotes because we're talking about capacitance, not ohms of resistance. It is like resistors in parallel. Okay, so far so good. One more page here for today. We're going to take a look at what happens when you start comparing capacitors that are side by side, that are in parallel. or comparing them when they're in series. Just take a look at what's happening with all the values for Q and for V. So let's start looking at these combined stories. Going to throw some wires on this deal here. Let's make these be some capacitors that are going to be connected up in parallel to this battery. There we go, we're connected. And I'm going to throw some numbers at this just so we can see what happens here. Let's say this is 4 farads and this is 8 farads. It's got a bigger parking lot to it. And I would like to use a 12-volt battery to try to drive some charge on there. What you're going to find is this smaller parking lot builds up a little bit of charge, but the bigger parking lot obviously builds up more. And we've got our corresponding negative charges as well. In this situation here, much like resistors when they were connected in parallel, you're going to find that you have the same voltage on both of these capacitors. Once they're fully charged, they're each going to be charged up to 12 volts. Okay, well, the guiding idea for this page is the relationship between how much Q you can put on a capacitor with a given amount of voltage that you can use to push it there. Well, we're using the same amount of voltage push, 12 volts, on both of these stories here. So let's go and take a look and see what happens to each of these stories. For that 4 farad capacitor, if I look at Q is equal to CV, the amount of Q there would be the capacitance. I've made up this number of 4. 4 farads is a huge capacitance, by the way. Multiplied by 12 volts, the Q on that smaller capacitor is 48 coulombs of charge. Pretty impressive, right? That we've stored up that much charge on that little parking lot. Okay, what about the bigger capacitor? Well, I'm going to play with CV again. Here, I've got 8 farads of capacitance and still a 12-volt push. And what you'll find is the Q here is going to be 96 coulombs. So they have the identical voltage, but they have Qs that are in proportion, in terms of ratios, in proportion to their capacitance. The larger capacitance has the larger Q to it. All right, well, let's compare and contrast that to this story down below. What if we start wiring these things up, this time now in series? Take a look at what happens. I would still like to have this smaller capacitance be 4 farads, and we'll make this one 8 farads. And we'll still make this a 12-volt battery. Okay, we'll grab some wire. We're going to connect up there, and then we'll connect up that little electrical island, and then we'll connect up this plate all the way back to the battery. Now remember what we talked about when we were looking at capacitors that were in series. Because that center section is a little island, you're going to see the exact same amount of Q on this capacitor as you do there. Those two plates have to have the same amount of charge on them. So whatever charge you put on this plate, you're going to find that you've got the corresponding amount there, and then we'll get these little mirrored charges where we'll have a negative charge here and a positive charge there. And all of those Q values will be the same. Well, what we can do now is figure out what the total amount of capacitance is. So I'm just going to go and double check that. 1 over this total capacitance, you could call it CT for C total or CS for series. It would be 1 over 4 plus 1 over 8. Okay, I'm just going to fire up my calculator here and see exactly how much that is. So 4 flipped plus 8 flipped, and then we'll flip that back. Okay, I think that's a nice little math fraction here somewhere. All right, 8/3. Okay, so we have 8/3 for our total capacitance. That many farads. Fantastic. Let's look at this thing globally for a minute. Globally, on the big picture, okay, we're going to be putting 12 volts on this story, and we've got 8/3 for our capacitance. Okay, so let's go with the whole picture. And we can say, all right, Q in total will equal capacitance in total times our total voltage. Well, we have 8/3 and 12 volts push. And when you check that out, you find the total amount of Q on every one of those plates is 32 coulombs. Every plate has that tiny little positive one, positive 32 coulombs. The tiny little negative one, negative 32 coulombs. The big positive, positive 32 coulombs. And the big negative, negative 32 coulombs. So everybody's just got this story here now of 32 coulombs. Well, let's take a look at what happens when we look at the individual equations. What happens when we go Q is equal to CV for each one of these plates? So the key thing when you're doing these in the future is you have to look at this and go, hey, they're in series. They have the same Q on them, right? That's kind of the key thing. And that's kind of like saying they have the same current in them, right? When you say they have the same Q. And I say that like as you relate it back to your knowledge of circuits with resistors. So we have 32 for our Q for sure. Very much like playing around with series resistors saying, oh, well, let's put in the current that we know and we'll do Ohm's law. The capacitance for that small one is only 4. So there's a voltage that's going to be applied there to create that. And when you check out the voltage, you find it's 8 volts. Well, that's very interesting. That's more than half of our 12 volts that we've got available in this story. Now, what about this one? We're still going to have 32 coulombs, but it's a much easier parking lot to fill. It has a better capacitance, a better filling ability. And so how many volts will we use to push that Q on? Well, when you divide, you find it's only 4. So actually, in this story, you're going to see that because that's such an easier capacitor to fill, it doesn't consume as much voltage. The voltage drop on that capacitor would only be 4 volts, and that would be enough to get to your 32 coulombs, whereas we need double that when we've got half the capacitance. And that's where we're going to stop for our second to last day, and then we've just got a couple more pages for the last day.